Hello again. In this experiment, you will determine the molecular weight of a volatile liquid. But there is more. In doing this, you will be walking in the footsteps of Jean-Baptiste André Dumas, the discoverer of this method and a very important early developer of chemistry as we know it. In 1826, Dumas postulated that equal volumes of gas at a given temperature and pressure contain equal numbers of gas molecules. Now, using this concept over the next 25 years, he determined the atomic weights of about 30 elements, and included in that was the fact that the nominal atomic weight of hydrogen was 1, not the 2 that others had believed. With this simple concept in mind, and armed with the ideal gas law, which is the modern reincarnation of this Dumas logic, we can now follow Professor Dumas into the laboratory and determine the molecular weight of an unknown liquid. To make our measurements, we will use a 250 milliliter Erlenmeyer flask capped by an aluminum foil cap here. There's a small pinhole in the top of this aluminum foil which will allow the excess vapor to escape. We will put our unknown liquid into the flask and then heat this flask in a boiling water bath. The liquid will vaporize, the vapors will fill the flask, and when all the liquid is gone and the flask is filled with vapor, we will take the flask and cool it to condense the vapor. The condensed vapor will then be weighed. Initially, we need the weight of the empty Dumas flask. To do that, we will use the electronic analytical balance. Make sure, of course, when all the doors are closed here, the balance is level. Set the balance to 0. And then open the doors, put the flask on the balance pan, close the door, and weigh it. Having weighed the flask, we'll now remove the cap, put in about 5 milliliters of your unknown, and then replace the cap and snug it down carefully. The heating bath should be a 600 milliliter beaker with about 300 milliliters of water in it. It should be at the boiling point, and don't forget, use this large ring so that if something happens here, it's not going to fall off and spill scalding water all over you. Carefully put the Dumas flask with its liquid contents into the boiling water bath so it is almost completely covered and is slightly tilted. Keep heating until the liquid is completely evaporated. Do not remove the flask from the boiling water bath at any time during this process. To see if there's any liquid left in the Dumas flask, since it's tilted, just wiggle the flask. If you see ripples, there's still some liquid left. After all the liquid is evaporated, continue heating for an additional 1 to 4 minutes. You should vary this for the different trials. Remember, you're trying to heat the vapor to the temperature of the boiling water. So you should be getting the temperature of this boiling water at this point. Finally, remove the Dumas flask and rapidly cool it in cold running water to condense the unknown vapors. Do not cool it below the dew point. Otherwise, you'll not only condense the vapors, but you'll also condense some atmospheric water. After cooling, dry off the flask and weigh immediately. As you can see, evaporation of the condensed liquid produces a significant change in the weight with time. Use the initial weight. You can dry out the flask by drawing a vacuum through the flask. The unknowns are very volatile and they will dry out very rapidly. After you have 3 acceptable runs where the mass of the condensed vapor varies by no more than 1/10 of a gram or less, you will determine the exact volume of your Dumas flask. And to do that, what you will do is you'll weigh the amount of water that this flask can contain. Well, here's the weight of the empty flask, which is 125.49 grams. Fill the flask to the top with water and then re-weigh it. 390.41 grams. You'll need the temperature of this water, which is 24.0 degrees centigrade. Here's the pressure in millimeters of mercury. The Dumas method is used to get molecular weights of pure volatile liquids. In our modification, we need those liquids to have boiling points below 100 degrees and a very low vapor pressure at 25 degrees. But I'm sure you should be able to figure out modifications which can get around these limitations. After completing 3 satisfactory trials, you can make your calculations. Our unknown in this video was chloroform, and our data allows us to calculate the mass of the vapor which was condensed, as well as the volume of the vapor from which this mass was condensed. This results in a molecular weight of 120, which is in excellent agreement with the actual molecular weight of chloroform. Well, that covers the main points of this experiment, but remember, this one is something special. This is not just about the grade. This one is for Jean-Baptiste André Dumas. So go to the laboratory and let's make him proud.